In this video, we're going to look at compartmental analysis, which is something that's very common in biopharma, pharmacokinetics, drug studies in general. We're going to look at it in a more simplified model, looking at an aquarium. But the idea is that you might have various compartments in a system. One might be the blood system, one might be various organs, and there might be flow of a compound into and out of these compartments. And we would know something about the rate of flow between them. What we want to do is predict what are the levels of a drug or a toxin in those various systems over time. And guess what? That prediction over time will be the solution to a differential equation where the model comes out of looking at how these rates interact. We're going to start with a simpler model, a single compartment, and that'll be an aquarium. So we have an aquarium like so. It has a certain volume, 25 cubic meters of water, and what we have is a pipe system where water is being pumped into and out of the aquarium. It's coming in, and it's important to recognize the various pieces of this and quantify them in terms of the kind of material they are as well, 10 cubic meters per day. We also have water flowing out at 10 cubic meters per day, otherwise we would either be emptying the tank or overflowing the tank. However, what we also have coming in with the water is ammonia, and it's coming in at a concentration of 150 grams per cubic meter. So what we see is that we're going to get ammonia added here to the tank. The rate at which it's going to be added is going to depend on how fast the water's flowing in and the concentration of the water. We're going to start off with a clean aquarium. At t equals 0, the ammonia level is going to be 0. We're going to start by finding out the rate of the ammonia entering the tank in grams per day. Well, that rate in is going to be in grams per day, so the units give us a huge hint in these kinds of problems. If we have a rate in grams per day, clearly the concentration matters. So we're going to have 150, and that's grams per meter cubed. And importantly, it's grams per meter cubed of water. That sometimes helps to focus our attention. These are grams of ammonia in meter cubed of water. And so what we would do if we want to get rid of this meters cubed is we would multiply by how many meters cubed of water do we have? Well, you have 10 meter cubed of water per day. Cancel our units, we get grams per day, and so we are gaining 1,500 grams per day. Perfect. We now know how much ammonia is flowing into this tank. However, that's not the only influence. As water leaves, initially it's going to be clean water, but as this water in the tank itself gains ammonia, some of the water flowing out is going to take some of that ammonia away. So this is not going to go just straight up at 15 grams per day every day. Some of it's going to get washed away with the outflow. That's our next step, and that's to look at that outflow and how it is going to affect the rate of ammonia level changing. We have water leaving at 10 cubic meters of water per day. And if that's the case, how much ammonia is leaving with it? Well, we need the concentration. Well, the concentration in here is not always the same. It starts off at 0. So the initial, imagine taking buckets of water rather than the flow. At the first second, if I scooped up 10 cubic meters of water and dumped it out, it would have 0 ammonia in it. The next day, though, there's going to be more ammonia dissolved in there, and I'm going to take more ammonia then with me. Well, if we define S of T as the grams of ammonia in here, then the concentration, which is what we had on the last page, we had ammonia concentration, grams per cubic meter. The concentration is going to be our amount S of T, which changes, but it's dissolved in the tank size. Whatever the total number of grams is, it's going to be dissolved in the 25 cubic meters of this tank. Cubic meters of water. Well then the rate out of ammonia out is going to equal this concentration, which is S of T. We're just going to call it S. We typically don't show the T's at this point. We know the amount of ammonia is changing. It's going to be S over 25 times the 10 cubic meters per day. Check the units. S is in grams, 25 liters, 25 is in meters cubed of water. And the 10 is cubic meters of water per day. And what do we end up with? We end up with grams per day of ammonia. Perfect. So this is a little trickier than the inflow, but it has a nice structure to it that relates to the inflow. We just need to write things out as concentrations. Of course, once we have those two pieces, ds dt, which is the net rate of change of ammonia, leave that unsaid here, that's going to equal the rate in minus the rate out. And we have just found both of those ingredients. ds dt is going to equal 1500 in every day for sure, minus, depending on how much we currently have, S over 25 times 10 as the rate of ammonia leaving the system. So that's quite a nice model. It captures everything we know about the system. It reflects the fact that the outflow is going to take more or less ammonia with it over time, depending on how concentrated or how toxic the water is in the tank itself. What we'd really be interested, though, is tracking the concentrations. So we're going to do a little adaptation here, noting that S is in grams. What we'd like to model, though, because it's easier to measure in most scenarios, is C in grams per cubic meter. We'd like to convert from this to this. How can we do that? Well, the concentration, we already talked about this, is the total amount of ammonia divided by the total tank volume. S is in grams, 25 is the cubic meters of tank volume. And so we can look at those, and we can also take a derivative of this if we like, thinking back to implicit derivatives. We can take the time derivative of both sides. The 1 over 25 is a constant, and the ds dt would just be the derivative of the amount with respect to time, amount of ammonia with respect to time. So if we want dc dt, we can just use this formula here. So the rate of concentration change over time is 1 over 25 times this expression here, because that's ds dt. 1500 minus S over 25 times 10. Perfect, that's all true. A bit annoying that we have a mix of variables, so what we'd like to do is convert this S into a C, but, oh wait, S over 25 is exactly equal to concentration. In fact, that's how we used it in our model. So we can actually model the rate of change of the concentration as 1 over 25 times 1500 minus 10 Cs. We can expand that in if we want. I'd leave it right like that for now. That is the rate of change of the concentration over time, which will let us predict if we can solve that differential equation. It'll let us solve for how quickly the concentration is going up to some nasty, unsafe level in the aquarium. The foundation of it, though, is starting with amounts, because they tend to be easier to think about and track, and focusing on how quickly things are coming in and then going out.